orgánico, también sustancias húmedas, por ejemplo, de materiales, siempre con componentes del suelo, y ella es especialista en la parte de cálculos que han visto ahí dando vuelta con el modelo Easy Music y otro tipo de modelos. Ella es especialista en eso, y también en espectroscopía, la parte de sincrotrón, SAS y técnica de sincrotrón. Se dedica a hacer esas cosas, metales pesados principalmente, con material inorgánico y material orgánico. And she's also a very good dancer. So in the list of dancers, after Minxia, she's the second one. Very great, Graciela.
Okay, thank you. I'm very glad to have the chance to share my work. And my work is to the human substance is another soil active component. So my title is the lead binding to human substance with the microdose modeling and spectroscopy. And this is the outline of the presentation. Actually, this two part is very important in this is the study. And let's go to the research background. Humic acid is a very important natural organic matter in the natural environment, such as in the soil, water, and sediment. And it is very important for the soil fertility, soil buffering, and carbon sequestration. And there is a large number of the function group on the human substance, but the calcitic and the phenolic group is dominant. And also there is also have some redox function groups like the phenolic and the structure. And the human substance with a very high redox active because and they have some quality groups on each. And due to the proton dissociation of the functional groups, so the human substance with a large number of negative charge. So the human substance has a high quality and absorption capacity to the heavy metals. And in the soil, the human substance is not very high. The mass. But it is very important for the heavy metal binding and distribution because the affinity is very high and the capacity is the most high. And so the human substance controls the heavy metals mobility, viability, and toxicity. And so we can see if the heavy metal binding to the solid organic matter, the bioavailability will decrease. So the arc of the group will decrease. And if the metal binding to the dissolved organic matter, it will move by the water. And also, if it is in the panic soil or in the wetland soil, and the oxygen is limited, and the human substance is reduced at these conditions, and the heavy metal like the acid will be reduced by the human substance, and at these conditions, and the acid will be formed, and it has a high toxic. So in the soil or in a natural environment, we need to know what happened, how the human substance bind with the heavy metal, because the species of the heavy metal have controlled his risk, his health risk in the nature. So we know that in the soil or in the sediment, the conditions is very complex, and the heavy metal binding to the human substance will vary with these conditions. So we need a reliable model to describe this binding. And in these models, the Nikan model is very tricky because he based a simple equations. And a large number of studies use this model to describe the highway binding to the chemical substance such as the calcium, cadmium, and lead. And based on this study, and the research derived a set of generic parameters to the human substance. So with this set of parameters, the model can be used to predict the environmental species in the nature. But we find a phenomenon because in the rainy soil we find the model can predict the lead by the cadmium binding, the zinc binding, nickel binding, and some environmental binding well. But for the lead, we can see this is in the soil model, and this is the clay soil. And in this soil, the free lead concentration also overestimated by the model. So why the model can't accurately predict the lead species? And we also checked the database of the generic parameter. We find when the research derived the generic parameters, the data, most of the data is from the humic acid, but not the soil acid. So this means that the generic parameter is also somewhat material species. So the aim of this study is that we want to know the molecular mechanism of lead binding to the human substance, and we want to find a method to improve the prediction of the model with the generic parameters. And then also in the candy soil, this is a oxygen limited. We want to know the effect of reaction, how to the reduction affect the lead binding to the human substance. So at the beginning, I want to give a brief introduction of the modeling. And the lead model is based on a simple binding equation, the Nickel equation, to describe the specific absorption, and plus a Doppler model to account for the electron interactions. And for the Nickel model, it assumes that there are two types of groups on the human substance, and the chemical heterogeneity can be accounted for a condition affinity distribution. And this is the Nickel equation. And in the equation, the Q is the set density of the functional solution, and the K is the affinity constant, and the P is the heterogeneity parameters. And the Doppler model was used to describe the electric binding, and it thinks the human substance is a drawback with a center value called the donor value. And in the donor value, the charged side can be neutralized by the salt ions. And throughout these values, there is a unified average electrostatic potential called the donor potential, and the donor value is dependent on the ionic strength. And in this model, the V is the only one that adjusts the parameters. So let's go to the lead binding to the human substance. In this study, we used two samples, and three of them is extracted and provided from the soil. And the reference human substance is purified from the solid human batch. And it was purchased from the Sigma outreach company. And we can see the carbon fraction of the folic acid is lower than the humic acid, and the mole ratio of the oxygen to carbon is higher than humic acid. This means that the folic acid will have higher the oxygen function density. And in this part, we use three experiment, the acid-base titration for the surface charge and the lead titration for the lead binding, and in this experiment, the free lead concentration was measured by the iron selective electrode. And the X-ray adsorption fine spectroscopy depth was used to study the lead correlations. And the samples for this experiment was prepared at pH 5, and the lead adsorption capacity is 1.3 and 1.8 for Xiong and folic acid. So this is very high. This very high lead concentration is we want to get a strong signal of the dust. So this is the result of the titration and the surface charge curves, and we can see the folic acid has the high surface charge electric density of the folic acid, and this is the model parameter, and the log K and the Qmax is different from the folic acid, and B is bigger than that. This means that the folic acid, the molecule size is small. And we also use the generic parameters to predict the protein binding to the samples, and this is the result. And we can see that the model can give the good prediction for the reference Xiong acid, because this Xiong acid is originated from the lignite. And but for the soil Xiong substance, that's built. So why? We can find the big difference between the prediction and the measured result is the position of the health, but not the shapes, because the shapes is very similar. So we have said that maybe we adjust the set density of the capacity. Maybe the prediction of the model will improve. So this is the result of the testing, and the result shows that when we use the computer group by adjusting these groups, and the model prediction is well. And this is the folic acid, but for the Xiong acid, but for the folic acid, it's not very good, but it becomes better. And this is the result of lead binding to the Xiong standard. The point is the experiment data, and the line is the model prediction. And with the increasing pH and the lead concentration, the adsorption is increased. And so the model parameters for lead binding is here, and you can see that for the soil folic acid and soil Xiong acid in both the reference, and this value is very high, higher than the generic parameters. And this high value will lead to a higher ratio of the NP1 to N proton 1. And this ratio indicates the manner of the lead binding to the toxic group is more density. And then we also use the generic parameters to prediction the lead binding to the Xiong substance, and refine it. It just give a good description for the reference Xiong substance, but for the soil Xiong substance at the low pH concentration, it always limits the binding, and this is very similar with the model in the soil. So we do a series of the sensitive tests, and we want to find the key parameters to improve the prediction. And the result tell us the generic NP1 was replaced by the specific value 0.92. The model prediction can be improved strongly. So the third is for the coordination environment or link. And the big A and big B is the different data conversion of the results. And in the big B, we can find there is two key on this spectrum. And the first bit is for the association of the lead oxygen shell. And the second is for the lead carbon shell. And you can find, because in this experiment, the lead nitrogen is used as a reference samples. And in this context, there is a low lead carbon shells. So for the reference samples, there is no the second case. So these two things tell us the lead binding to the humic acid is to form a inner sphere complex with a carbon-oxygen lead structure. And then we're fitting coordination. And this is the result. In this table, this is the distance between the origin, oxygen and the carbon the distance between different atoms. Now the first one is for the lead and the oxygen, and the shell 2 is the lead to carbon. And the Cn means the coordination number. And so you can find that for the first shell, the coordination number is 4, is about 4. But for the shell 2, the coordination number is 2. This means that when the lead binds to the humic substance, the carbon-oxygen lead oxygen carbon structure was formed. And we also find that there is some difference in value of the coordination number, but there's a low distinct difference between the humic substance. So we think the possible species on the lead binding is like this. And according to the depth, maybe the bidentate species will form. So like A, B, this one and E. But we know that the 5-member rings and 6-member rings is stable. So we think the lead binding to the humic substance, when he binding, he is with 2 carboxylic or 1 carboxylic and 1 chaotic groups. So this is the binding structure. So below the humic substance can reduce the oxygen leakage. So in this section, we want to know how the reduction to affect the lead binding to the humic substance. In this study, only 2 samples was used. This sample was also used in the form part. And the reference humic acid is the peak humic acid is purchased from the International Humic Substance Society. And this is the result of the elemental content and the carboxylic site and the group site density. And we can see that the peak humic acid has a higher ratio of the carbon to hydrogen, and the function site density is high. In this part, we have 4 experiments. The first is the reduction experiment. The humic substance was reduced by the direct electrochemical reductions. And then the acid-base titration and the lead titration was used to study the surface charge and the lead binding. And these three experiments was carried out in the glove box because we need an analytical morphism. And then the synchronous fluorescence spectrum was used to study the absorption mechanism. And during the reductions, and the phenol groups will reduce to form phenol groups, and during this reduction, the current and the pH of the solution we record and use this the current. We can calculate the transfer electron capacity, and this is the result. And the ketonic acid is 0.9. It's higher than the soil humic acid because it has the high ratio of the carbon to hydrogen. So this is the spectra, and you can find there is two peaks on the spectra, and the first one is for the forward light fraction, and the second one is the humic light fraction. You can find the change of the signal is more and for the fraction, the humic fraction. This means that the point growth is on these fractions. And so, because during the reduction, the phenolic groups form, so we can find at pH, when the pH is less than 5, the negative charge on the humic substance has increased. And at the low pH, when the pH found lower than 5, that's very similar. It's because the phenolic group has the high affinity. And this is the result of the model parameters of the proton binding. We can find the cell density of the phenolic increase, and the organic parameters also change. And we find that for the calcifer, the cell density is also the same, but these parameters and affinity constants change a little because the phenolic group will change the chemical structure of the humic substance. So this parameters value will be changed, but it's not big. And the phenolic group increase and the surface charge increase. This will change the lead binding. But we can see in this figure, the red point is the result of the reduction humic acid, and the black one is for the untreated humic substance. At the low lead concentration, they are very similar with each other. And actually, at the high concentration, the difference is big. But because in here, the lead was carried at the low, so this is not very obvious. But when if we calculate the maximum absorption capacity, we find this value is very higher than the untreated one. So we do the Nickel-Donner model, and we find for the lead binding, the parameters very similar. This means that the reduction only affects the maximum absorption capacity, but not affect the lead binding at the low concentration. So we use these parameters. We also calculate the lead species. And in these figures, the black one is the species of the untreated humic acid, and the red one for the reduced humic acid. You can see for the peeled humic acid, the red one and the black one over with each other. And in this one, for the soil humic acid, the lead binding to the phenolic groups of the reduced humic acid slightly increased. And we also used the spectra with the purely cost analysis to find the lead binding mechanism. And the left figure is the differential spectra, and this is the purely cost. And we find with the increased pH and the increased lead concentration, more and more lead bind to the humic-like fractions, and compare the untreated humic acid and the reduced humic acid. The spectra is very similar with each other. This means that the lead binding to the humic acid and to the reduced humic acid, the mechanism is similar with the untreated humic acid, and those are the lead are changed by the periodic growth of the humic-like fractions. So let's go to the conclusions. And in this study, we find that you use the specific NP1 replace the generic NPD1. We can improve the prediction of the model strongly, and the model parameters related with the depth show that at the low concentration, the lead binding is more density, and at the high concentration, the binding density. And when the humic substance reduced, and you can find the function groups increased 12% to 40%, and the maximum absorption capacity increased 9% to 40%, and the proton binding parameters become high. But we also find the lead binding parameters is very similar with each other, and the lead species of the reduced humic acid and the untreated humic acid very similar with each other, and the mechanism is the lead mechanism is the same. So we think the reductions will dump affect the lead binding to the humic substance in the later systems, because in the later systems the lead levels is very low, and the modified generic parameters can use it to predict the lead species at the belonging soil, because the reductions will not change the lead binding. Thank you. This is my
Preguntas.
okay.
Maximiliano.
Sorry, very next talk. My English is not good, but I have two questions.
Okay.
The humic and fluidic acids that we use are in the solid form or in the
Yes.
solid form.
So
But you talk in your talk, you said absorption, and I don't know if the humic and fluidic acid are in solid or the solid form.
the humic acid and the folic acid before the experiment is dissolved in the solution. It's not the solid. It's like a gel.
Okay.
Yeah.
The experiment, the model we can
Which one?
predict the possible dissolution of unit fraction or inverse, the aggregation in the presence of metal ions.
You mean in the experiment, the Xiong acid may be aggregation. Yeah.
Yes.
Yes, I found this phenomenon. Especially for the lead binding, when the experiment over, you find it can be down in the cell. Yeah, it's a aggregation.
Okay.
Yeah, because the lead is positive and the Xiong acid is negative, so the particles.
I know that calcium ions produce aggregation of dissolved unit fraction. The question is, see, the metal ions that we study produce the same aggregation or relation of the dissolved unit fraction. And then see the model predict this aggregation, because the model, I understand that predict the binding between the metal and carboxylic or phenolic groups of unit.
Maybe.
But I don't understand if the model predict a possible aggregation or relation. So the first question is if the study, the unit or fluid is in the dissolved form or in the solid form when you study at the presence of the metal ions. The experimental is you use the unit in the solid form or in the solid form when you study the presence of metal ions. To study the binding.
If your humic substances were dissolved,
Yeah,
or
it's
solid,
dissolved.
you
Yes.
first dissolve.
Yes.
First dissolve that in solution,
But
and
at
then you
the
can study.
dissolved. Yes.
But then sometimes if you are too much late, it coagulates a bit or it precipitates. And what he was asking is, if you can predict with your model coagulation and precipitation, can you predict that with the NICA model?
Yeah.
You can. So you can say whether it's going to precipitate at this pH or at this concentration.
The aggregation is only find at pH 4.
Okay.
Yeah. At pH 6 and pH 7, there is no aggregation.
And you can predict that with the model, that it aggregates at pH 4 and not at pH 5?
Actually, in the model,
No,
I can't.
you can.
Yes.
Yeah. With the model, you predict the binding.
Yeah.
Yeah, but not precipitation. Yes.
Yeah. But the aggregation is actually
Yeah, taking place.
confined in the experiment. But it's at the low pH and high lead concentration.
Another question?
Hi, when I stop